Hi there and welcome to our latest edition of our P4 Radiation for Life topic, and today we're looking at nuclear fission. So here we'll have a look at our objectives. I will see you at the end. Bye bye. Okay, so looking at nuclear fission, we'll be looking at, by the end of this lesson you should know and understand how nuclear fission can be used to generate electricity, and what happens when an atom undergoes fission. The term nuclear fission means nucleus splitting. So all it means is that we have a nucleus that splits into two nuclei. Now if we have a look at what it actually does, we can look at this diagram here. Now when a neutron is fired into a nuclei, normally a big nuclei such as this uranium nucleus, what happens is this addition of the neutron causes this to become unstable. Now as it becomes unstable, it starts to split. Now as it starts to split, we get energy released here. Now the value for the energy that's released is equal to Einstein's equation of E equals mc squared, where m is the mass that's lost and c is the speed of light squared, and that will give you your value for energy. Now this is actually quite a useful process. Now the term nuclear makes it sound like it could be very dangerous. The association with nuclear bombs gives it that connotation, but nuclear fission is really very helpful for us. So how does nuclear fission become helpful to us everyday people? Now what happens is, as we've seen earlier on in the smaller scale, we have a neutron that fires into a uranium nuclei. That uranium nuclei splits to form a barium and a krypton nuclei, and then this causes three further neutrons to be released. Now this neutron hits another uranium, forming another barium and krypton nuclei, and we get again even more. This one hits another one and we get more. This hits another one and gets more. So here we've got one neutron that gives out, after just two rounds of splitting, we've got one neutron that gives 1, 2, 3, 4, 5, 6, 7, 8, 9 neutrons that can go on and further react again. Now this is what we call a chain reaction. Now you can imagine the amount of energy that we get here is then trebled by the time we get to here. Now if we're thinking about how much uranium we've actually got, we might have a very large sample of uranium. Now this is where the problems come aboard with this. Now if we had no control over this reaction, then this energy would obviously just keep trebling and trebling, and it would become uncontrollable. Now when it's uncontrollable, it's gone out of control, this is what happens during a nuclear explosion, during a nuclear bomb, and this is where you get a vast amount of energy released in a very short time. Now the fact that we can control this means that it's able to be used as an energy source. So we've obviously seen what happens to the actual nuclei. Now what we'll do now is we'll have a look at the reaction. Now we've seen that one neutron will collide with a uranium nuclei. So we have here our one neutron colliding with our uranium nuclei. Now you can see here we've got the bottom numbers here, which are the atomic number. Now obviously it's a neutron, so we don't have any protons, whereas this one has 92 protons. Now these protons split, not equally, but you've got krypton and barium. Now at the top we've got the masses. Now the masses here should add up to 239 on both sides. Now we can see here that here we've got our three neutrons that carry on and can collide with further uranium nuclei. So we get multiples of this reaction happening. So how can we use this to generate electricity? Now, here we've got a diagram of a nuclear power station. Now you may recognise the end parts as being very similar to a coal-powered power station. Now here we have the nuclear reactor. Now this is where the reaction that we've seen already, this is where this is occurring. So we've got the neutrons colliding with uranium, splitting, and we're getting all this energy. Now this energy can cause the water or a sort of liquid to be heated, and what this can do is this can go into a heat exchanger. So the energy produced here can produce water in the form of steam, which can turn a turbine. Now the turbine turns a generator, and here we get the step-up transformer that puts the electricity into the national grid. Now how do we stop this becoming a uncontrollable reaction and having some sort of nuclear explosion? Now here you can see boron rods. Now the boron rods, what they do is they absorb any excess neutrons. Now what they do is they absorb the neutrons that are produced here, so they can't react further with any more uranium. Now what this can do is it can slow the reaction down. Now you can move the boron rods in and out depending on how quickly you want the reaction to go ahead. So if you want a fast reaction, you move them out. If you want to slow it down, you move them in. Okay, so we have looked at the nuclear fission and how the nuclear fission reaction happens, where we get the neutron colliding with a unstable uranium nuclei to make it even more unstable, so it splits to form two smaller nuclei. We also get the extra neutrons that are produced that can go on and collide further and further and further. We've also looked at how that can be used to generate electricity in a power station. Anyway, I hope you've enjoyed this video, and I will see you next time. Bye bye.